as far on this as we can today. I don't know exactly how far we'll get, so we'll just see. We're going to talk about electrons and atoms. This gets fairly complicated fairly quickly. The good news for you is you don't have to know all of the really complicated stuff, but I'm going to tell it to you anyway because I think it's kind of cool. Yeah, definition of chemistry is fast, complicated. Yeah, it's all made up. No, I'm just joking. It's not. Well, some of it might be. I don't know. All right, so we're going to talk about electrons now, and this gets really weird because electrons are just strange, very, very strange. They do strange things. We don't completely understand what electrons do. So, and really, most of the debate about the atomic models for the last 100 years has centered around what are electrons doing exactly inside of atoms. Okay, that's the part we really don't understand completely. So electrons are extremely small particles that have some mass, okay? Not a lot of mass, but they have some mass. They have a charge of -1. Okay, now that's a relative charge. That's the way we usually measure charges in coulombs. And if you were talking about this in coulombs, it would be a much smaller number than this. Okay, but we assign it a charge of -1. Do you know what charge a proton has? A +1, okay? So proton, you have one proton, one electron, they balance each other out, +1 and a -1, so it's neutral at that point, okay? If you have the same number of protons and electrons, the atom is neutral. We've talked about that before. Okay, so they have an electric charge of -1. They move around, well, who knows, really, okay? We'll call it a wave-like fashion, sure. They kind of act like particles, kind of act like waves. That's what makes these so complicated. Because usually in our everyday life, we're used to classifying things in one of two ways in science. We're used to classifying it either as matter, something that has mass, okay? All of you, the table, the chairs, everything in this room, basically that we can see, has mass, okay? So we would call it matter. And then energy is kind of the other major classification of stuff, right? So energy would be the radiation coming from the sun, or, kinetic energy, potential energy, those sorts of things. Sound energy, light energy, heat energy, all of those. Okay, so anything that doesn't have mass, we usually classify as energy. Well, now you've got these weird things, these electrons. They have some mass, but then they kind of act like waves also, which waves we usually associate with energy. Okay, so are they mass? Are they energy? They kind of act like both at the same time. Okay. They can be found in what's called orbitals in the electron cloud. Now here's where, let's see. Yeah, I guess we're going to get into the quantum model a little bit later. But I'll tell you what, let me give you just a little bit of background right now. So when I say orbitals, okay, this is where I have to fill you in a little bit on the part of the video that we didn't get to finish the other day. You remember Heisenberg on the video? Okay, the Heisenberg uncertainty principle is what he came up with. And the idea behind uncertainty was, remember, he said that you cannot ever conclusively say where an electron is at any given time. Okay? And he said that. Does anyone remember why he said that? When you look at them, they move, right? Okay, so in order for me to see you in this class, it's because light is bouncing off of you and hitting my eyes, right? We don't really have any other way to detect something other than, well, one, if you can touch it or feel it, right? Okay, that's one thing. But obviously the atom is too small for us to do that. The only other way we really have to detect things is to bounce electromagnetic radiation off of it and see what it looks like, okay? The problem is, when we hit electrons with light, they're so small, they move. The light is actually, it has enough energy to move the electrons, okay? So when we hit it with light, now the electron is somewhere else. Whoops. Now we don't know where it is anymore, okay? We know kind of where it was, but now we don't know where it is, okay? So that's what Heisenberg said. He said you cannot know for sure where an electron is, all right? So the Bohr model, remember the Bohr model kind of looks like this, okay? The assumption here is these things move in orbitals, in orbits around the atom, okay? What Heisenberg said was, no, we can't really draw a picture like this. This doesn't work because we don't know where the electrons are. What we have to do instead, the best we can do, is say that they're in these regions of probabilities, kind of what they called it, okay? And the best way that I can, I don't think I told you this analogy the other day. Maybe I did, actually. Seems like I've said this year. Anyway, if I go outside of this room and the window is covered, and someone asks me, where are your students? What's the best that I can say? Yeah, in the room, right? If they ask me specifically, where are you in the room? Okay, where's Drew in the room? I don't know, because I can't see in, right? But I know you're in here somewhere. And that's kind of the best we can do with electrons. We can say, okay, they're in this general area. I don't know exactly where they are in there. I don't have any idea what they're doing in there, okay? But that's where they are. Does that make sense? So that room we call an orbital, okay? That's an orbital. It's an area where the electron most likely is, okay? And that's the best we can do, even with all of our modern technology, even with the technology that lets us see individual atoms. The best we can do with electrons is say that they're probably in this region, okay? So that's what an orbital is. And electrons are responsible for light. Now, you remember that from the video? Remember the hotels? Yeah. The hotel? Right. So the electrons are dropping from one energy level to another. Depending on how far they drop, they give off a certain wavelength or frequency of light.
So if they give off the light, and once they give it off, when they move again, if the light moves them?
Okay, so if they give off light, the question was, if they give off light, wouldn't they move again because the light moves them? There's one of two things that can happen to an electron. Either you hit it with light and it moves, okay? So if you hit an electron with light, guess where it's going to go? And again, I'm going to use the Bohr model for this. I shouldn't have erased this, I guess. Let's say you've got an electron right here, okay? If you hit that electron with light, it's going to jump up to a higher energy level. It may go up to here. Does that make sense? So now it's further from the nucleus. When it gives off light, it's going to drop down closer to the nucleus, okay? So what happens is you hit this thing with light. Temporarily, it jumps up to a higher energy level, okay? Then it drops back down, and when it does that, it gives off light, and we can see that. So the electrons are either absorbing light and jumping up to a higher energy level, or they're giving off light and jumping down. Does that make sense? Okay. And remember, these jumps that happen, they're like the rungs of a ladder. The electron cannot be anywhere between these two energy levels, okay? You can't step in between the rungs of a ladder when you're climbing a ladder. You have to be on the rungs, okay? So that's kind of how these jumps work as well. But that's how electrons are responsible for light. I guess I kind of gave away some stuff that was on here. Okay, so let's fill out the notes on this. Light's a form of energy. We all knew that, right? Light coming from the sun, that's where we get pretty much all the energy on Earth. I say pretty much. That's where we get all the energy from. Other than, I suppose, if you... I don't know, never mind. Okay. Energy comes in small, measurable increments. That means it's quantized, okay? In other words, see, this is a hard concept, but basically energy exists in little packets, okay? I don't usually think of it that way, but if you keep dividing energy enough, you keep dividing it, keep dividing it, keep dividing it, eventually you're going to get down to a point where you can't divide energy any further, and that's a little packet of energy called a photon, okay? So what that means is light must be quantized, okay? So if energy is quantized, light must be quantized. And all that means is if something is quantized, you can't infinitely divide it. You guys ever heard that whole analogy of, like, you can never really get to that wall? If you just move halfway to the wall each time you move, you'll never get there, right? Because if I move halfway to the wall, let's say it's 10 feet away, I move halfway to the wall, now I'm 5 feet away, right? Okay, if I move halfway to the wall again, now I'm 2.5 feet away. Okay, if I move halfway again, see, I just keep moving half, 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 half. I'm never going to get there. Now, eventually, I'm going to be moving such a small distance you won't even be able to see it, right? But I will never make it to that wall if I'm just moving half the distance every time, okay? What they're saying, and again, like I said, some of this stuff is just, you know, a little bit mind-numbing. But don't worry about that, okay? I'll tell you what you really need to know. But the idea here is, with quantized energy, the idea is you could divide energy enough to essentially, at some point, you're going to get down to the smallest amount of energy, and then you can't divide it anymore, okay? So it's not like you can just keep dividing it forever and ever and ever. You divide it enough, and you get these little packets of energy, and the energy can't get any smaller than that, okay? That was the idea with quantized energy. Sorry. Smallest pieces of light are called photons. P-H-O-T-O-N-S. Kind of like, it's basically protons with an H instead of an R. Okay? Photons. I'll just trace over it. I don't know if this is going to work or not, actually. Oh yeah, that works pretty well. I didn't. I don't know why he put it in yellow, but yeah. I mean, yeah, I don't know why. Maybe so. Maybe you can see it better if you do that. I don't like to turn my lights off because then people fall asleep. So, okay. So these smallest pieces of lights, they're called photons. And you can think of a photon kind of like a little packet of light energy, okay? We usually think of light as being waves, but you can almost think of light as having this kind of particle-like quality to it. It's almost like it has mass because it can move things like electrons, okay? So it's weird. There's this whole blurring of, is it mass, is it energy? Is it matter, is it energy? So light you can think of as this stream of particles traveling in a wave-like fashion. Whatever that means. You know, at some point, I don't even understand this stuff, okay? So obviously I don't expect you to understand the things I don't understand. But it's pretty heady stuff. It's stuff that the best physicists in the world understand, sort of, but not the rest of us. Okay, so let's talk a little bit more about light, because if light is in these packets, and this light is going to help us to understand electrons ultimately, then we need to talk a little bit more about the light, okay? So, study of light led to the development of the quantum mechanical model, and all the quantum mechanical model is, that's the model I just told you that Heisenberg came up with, where it said we can't know exactly where the electrons are, so we have to just talk about where they probably are, okay? That's the orbital idea. Light is a kind of electromagnetic radiation. I'm pretty sure you guys have learned this before, haven't you? The electromagnetic spectrum. You guys remember talking about that? Maybe in 8th grade? I would guess is the last time. Okay. All right, so electromagnetic radiation, we're talking about gamma rays, X-rays, UV light, visible light, infrared, microwaves, radio waves. Is that ringing a bell? Any of that? Okay. That's the electromagnetic spectrum, okay? Gamma rays, X-rays, radio waves, etc. Visible light is kind of right in the middle of that spectrum, okay? So that's the only light we can see. Every other kind of light is actually invisible to us. We can't see it with our eyes. That doesn't mean it's not there, okay? That's the speed of light. Oh, actually, you have that part. Okay, so speed of light is 2.998 times 10 to the 8th meters per second, and it is abbreviated C. It's Latin. That's why it's not S, or L, it's C. Okay? That's really fast. In fact, that's as fast as anything can go. Ever. Period. That is the speed limit of the universe right there. Okay? According to Einstein, nothing can go faster than the speed of light. In fact, if you start to get close to the speed of light, time starts to slow down because you can't go faster than the speed of light. It only slows down for you, though. So if you're traveling at the speed of light and you know, 10 years out in space, you'll come back and you'll be younger than everyone else that was your age. Yeah. I'm telling you, this stuff is weird, okay? But it's cool. Yeah, if you like stuff like that, you should read Einstein's theory of relativity. Although, yeah. Oh yeah, Stephen. Yeah, it's hard to read some of those things. You might want to start somewhere lighter rather than Einstein's actual theory of relativity.
My mom was telling me that there's something like 100 people to Mars starting in life.
What? Say that again.
My mom was telling me because like her friend came over last night. And
Mm-hmm.
he was telling my mom that they're like sending, they're taking an application, but they're only taking like 100 people and going to Mars and they don't come back.
They're going to Mars. I hadn't heard that. I'm gonna have to look into that.
She was a lot.
Interesting.
They're taking one person and they weren't coming back.
Huh, okay. I'll have to look into that. All right.
I said you put an application.
It's like free, but you
Well, I might put in an application if that's really true. All right. Anyway.
I would not.
No, I'm not going to.
I never want to go to space.
Okay. So, back to this. The color of light. If you want to know the color of light, it's determined by the light's frequency. Now, when I say this, I'm talking about visible light, okay? Visible light is the only kind of light that has color. By the way, just another little fun fact. You girls have the advantage over us guys in the color area.
You guys are more likely to be colorblind, right?
Well, we're more likely to be colorblind for one thing, but then for another thing, you can actually, with your eyes, most females can see more of the visible spectrum than guys can. So on the two ends of the spectrum, girls can usually see a little bit better, a little bit more light than guys actually can. Okay, so I don't know if that's why you know all the names for the colors and the guys don't care, or you know, I don't know why that is, but you actually do have a biological advantage over us as far as seeing color. There's the electromagnetic spectrum, okay? So again, notice you've got all of these different types of electromagnetic radiation, and right in the middle of that we've got visible light, and it's in a very small little section right here, okay? That's all we can actually see. All the rest of this is here. It's all around us, but we can't see it, right? Now, not all of this is all around. Hopefully there's not too many gamma rays around you right now. But that radiation will kind of tear up your insides to pass it through you. Mutates your DNA, all that good stuff, causes cancer. No. DNA mutations are not cool in real life. They're only cool in comic books. So X-rays, we use those to see through people, right? Ultraviolet, where do you experience ultraviolet typically? Yeah, I mean, it comes from the sun. I mean, all of these ultimately come from the sun, right? But where we have to be careful with ultraviolet is that's the type of light that can cause us to have sunburns, okay? So you've got to wear sunscreen so that you don't get overexposed to UV light. Infrared, that's where heat given off by people gives off infrared radiation. That's why night vision goggles work, right? Night vision goggles can see infrared radiation, so they can see heat. That's why you can see things that are alive in the dark. Yeah.
Is that why, like, on a road, if it's really hot, you can see heat from off the road? Is that...
Oh, so the actual heat waves. I think what you're seeing there is the maybe some of the. I'm not sure exactly what you're seeing there. I'm gonna have to think about that.
Because I don't think it's water evaporation.
No, it's probably not because it's on a dry. It's in dry areas. I don't know. Let me think about that one. Radio waves, that's radio. And microwaves, we know microwaves. Okay, now, listen up. The further to the left on this spectrum that you go, the lower the energy of the light. Okay? Now, all of this can be called light. This is visible light, but it all can be considered light. Okay? Radio waves have the lowest energy. Gamma rays have the highest energy. that's why they mess with your body when they pass through you, because they have so much energy they mess up your cells when they go through. Okay. High energy, you're talking in the 380 nanometer range for visible light. Okay, so visible light goes anywhere from about 700 nanometers to 380 nanometers in wavelength. Okay, so now we need to talk about wavelength and frequency and all that stuff. Why is this not going? There we go. Okay, so the general parts of a wave. Have you guys talked about this before? You remember talking about this in 8th grade? Parts of a wave?
Yeah.
It might come back to you, okay?
Yes.
When we talk about wavelength, we're talking about the distance from the top of one wave to the top of another wave. That's your wavelength, okay? So just essentially how long is the wave as it's moving, okay? Oh, okay, I got you. Okay. So then I'm not too worried that you know amplitude, origin, crest, any of that stuff. Crest is the highest part of the wave. Oh, I see what you're saying, because everything is labeled. Let me wait until I get to one that I actually care about. Because I don't really care that you know the crest, the trough, all of that stuff on the wave, okay? Not that big a deal. I do want you to know wavelength, and I want you to know frequency. Those are the two major things that you need to know, okay? So the wavelength tells us the type of light. Depending on what wavelength it is will tell us, is it UV, is it microwaves, is it visible light, what is it? Okay? And then the frequency of light can tell us the different colors. Now the wavelength can tell us the color of light as well. Okay? Either the wavelength or the frequency. It's just kind of two different ways of looking at it. Okay? And then the amplitude is going to tell us the amount of energy that's found in the wave. And then wavelength and frequency are inversely related to one another. That means if the wavelength increases, the frequency decreases, and vice versa. Okay? You guys remember talking about inversely related, right? When we were talking about the gas laws. Remember, pressure and volume are inversely related. So when the pressure goes up, volume goes down. Okay? Same thing here, okay? They're inversely related, so if the wavelength goes up, frequency goes down. What's that? Smells like coffee. I have no explanation for that, other than there's probably coffee around. Okay, so electromagnetic radiation goes through space as a wave moving at the speed of light, okay? All electromagnetic radiation moves at the speed of light because it essentially is light, okay? So the equation for this, oh, no, we're not there yet. Okay, let me talk about wavelength versus frequency here for a second, okay? This kind of explains the inverse relationship. So your wavelength, from here to here, okay, if you have a longer wavelength like that top example, the frequency is less. And frequency just means how many waves go by you in a certain amount of time. Okay? So if I'm watching these waves go by, I'm going to see 1, 2, 3, 4 waves go by here, right? Okay? Wavelength's kind of long, the frequency's a little bit low. If the frequency's higher, that means more waves are going by me in a certain amount of time. So now I'm looking at 1, 2, 3, 4, 5, 6, 7, 8 waves going by in the same amount of time. That means that the wavelength, the distance from one crest to another crest, is a lot shorter. Does that make sense? Okay? So you have a higher frequency, that means a shorter wavelength. Okay? The waves actually get closer together. If you have a low frequency, the waves spread out a little bit, longer wavelength, and less waves go by you in the same amount of time. That's why they are inversely related to one another. Okay? Now the equation for this is the speed of light equals the wavelength times the frequency. Okay? I don't think we're going to do any calculations with that. We've got a lot of stuff still to cover before we take the final. So we'll just talk about this in theory, okay? But in case you're interested, the wavelength times the frequency equals the speed of light, okay? So then if you know one, you can calculate the other. So for example, if you know the frequency, like this example problem down here, it says calculate the wavelength of yellow light emitted by the sodium lamp shown. It's shown in here, I think, not. It's not shown here. Sorry. So basically, if you have the frequency, you can use the speed of light and the frequency to calculate the wavelength. Okay, you can get one from the other. Yeah, 2.998 times 10 to the 8th meters per second. Okay, which you don't have to memorize that number either, by the way. Okay, so let's go to the next page. We're not going to get too much further today. We'll try to get down to B. Okay. Yeah, I know. We've got a couple minutes left. And I like to talk about this stuff, so I tend to go through it a little bit slower than I probably should. Okay? Now, the energy of electromagnetic radiation is directly proportional to the frequency. Okay? So in other words, the higher the frequency, the higher the energy. If the frequency goes up, so does the energy. If frequency goes down, so does the energy. Okay? So they're directly proportional. Okay, and there's an equation that relates those as well. Energy equals, this is Planck's constant, which again, you don't need to know this, 6.626 times 10 to the negative 34th. And then the volume, or not volume, this looks like volume, but this is actually the frequency, okay? So because they're on opposite sides of the equation, if the energy goes up, so does the frequency. If the frequency goes down, so does the energy. They're directly related to one another, okay? Kind of like pressure and temperature are directly related, okay? All right. So E is energy in units of joules. H is Planck's constant. You don't really need to worry about that stuff because, again, we're not going to do calculations here, okay? So I wouldn't even worry too much about writing this down, other than maybe knowing that E is energy. And the V-looking thing is frequency. It would be good to know that. Okay? So, if you have a long wavelength is going to equal a low frequency. We already talked about that. That means low energy. Okay? So notice, that means the wavelength is actually inversely related to the energy as well, right? So if you've got long wavelength, in other words, the wavelength goes up, energy goes down. Okay? So those are inversely related as well. So then, if you have a short wavelength, that means it's a high frequency wave, high energy wave. Okay? We haven't really gotten anything yet that I think that I could really quiz you on. I guess there are a few things, but I don't think I'm going to have a quiz tomorrow. We'll probably save that for Monday. Yeah. So we'll just continue on these notes tomorrow because we will be here tomorrow.